Good evening and welcome to the extra session of the live interactive session of the Neural Science for Engineers. The course instructor is Professor Vikas V from NIMHANS, Bangalore. I am the PMRF teaching assistant Vikas Pandey from IIT Jodhpur. So, as previously discussed, that this is a brief about me. Now, as previously discussed, uh, in this session we will be seeing microsystems fabrication technology that is used to make the electrodes for the stimulating devices as well as the electrodes for ECG, EEG, and such devices where we are taking information from the brain. So this itself is a field of this itself is a very big field where a lot of work and lot of technology is involved. So we will just see a brief about it, what are the steps involved, and we will see how a simple sensor or a processor is made using this microsystems fabrication technology, or in short it is also called as the uh, microfabrication. Okay, so it is a miniaturized system realized on silicon wafer. This is in general, but as we have seen in case of stimulating electrodes and all, we can even now work on the flexible electrode. So the technology remains the same. Some modifications is there. So mostly most of the technology is developed over the silicon wafer, but uh, that can be adopted according to our use case. Okay, so it can be used to make a micro sensor, a micro actuator, or a mechanical or fluidic or flexible device. It is even used in making optical components or their combination with electronic circuit on same or different chip. Okay, so from where it starts. So if you see this, it all starts from silica, that is a shiny substance that is found along with sand. So its chemical formula is SiO2, same as the sand. From there, it is made into ingots, and it through this fabrication process, the microfabrication process, it becomes a processor, and then it goes into the electronics we use today. So this whole journey is facilitated by something called as microfabrication technology. So these are the wafer is made from SiO2 to wafer. That is a process that will involve CZ process and all. Will not go that details. We will see the process of converting this into electronic circuits or electrodes or sensors. Okay, and that can be incorporated into devices like mobile phones or sensor devices and this. Okay, so to start with, let's start what uh, is our base or substrate. In most of the microfabrication techniques, silicon wafer is the base. Silicon wafer is the place where we start. Okay, so if you buy a silicon wafer, if you buy a single piece, it will be like this, uh, one piece. Okay, in a single what you say, a single box, or you can even buy in an array of boxes. Like in the box, there will be array of wafers. So you see the silicon wafer have some cut marks. Like you see here, there is a cut mark here. Okay, these are used to identify what type of silicon wafer it is. We will not go into crystallography and the p-type and n-type. So in general, if you are from somewhat from engineering background, you must be aware that what is a n-type semiconductor, what is a p-type semiconductor, what is 100 plane and 111 plane, and these things. So in general, if we have a wafer that has a big cut here one side, and opposite to that there is a secondary cut, small cut, then it is a 100 plane n-type semiconductor. That wafer is n-type semiconductor. And then Similarly, if we have a secondary flat that is at 90 degrees to the primary flat, then it is a p-type semiconductor having 100 plane, 100 crystal orientation plane. Okay. Then, if the primary flat and secondary flat are separated by just 45 degrees, then it is in N-type, but 111 N-type. So, and in case there is only one primary flat, then it is 111 P-type. So, we can say that this wafer that is shown here, that is a 111 P-type wafer. Fine. So, once we have this wafer, where will we process this? Okay. This is very important, that in what environment this whole process should occur. That has to be very clean, that has to be contamination free. There should be no dust, there should be no particle contaminants. And to ensure this, there is something called as clean room. So clean rooms are the place where these microfabrication devices are made. All these microfabrication processes are done inside a clean room. So what is a clean room? It is an environment that is artificially made to ensure free from dust and other contaminants. Usually it is these clean rooms are there in manufacturing and electronic component industry, as well as in pharmaceutical industry. Then all the clean rooms cannot be same. Certainly if there are clean rooms, they cannot be the same throughout the world. So to ensure that they are same, or they at least follow some standard, some uh, there are some standards that are made for these clean rooms, and they are classified using the number and size of particles permitted per unit volume of area. So less the number of particles, the better will be the clean room, and better will be the throughput in a sense. Okay, so they are classified using two standards. One is US Fed standard, the other is ISO standard. Okay, so US Fed standard is like class 1, class 10, class 100, class 1000, class 10,000, and class 1 lakh. Okay, and this is based on the particle size of zero point 0.5 micrometer particle size in 1 cubic feet. Okay, since this is US standard, so they will follow the fit. Okay, so this is 0.5 micrometer particle size. How many 0.5 micrometer particles are allowed in a cubic feet? So if we take the 1 cubic feet air of the clean room at any place, it should have the maximum. If it is a class 1 clean room, it should have a maximum of only one particle of 0.5 micrometer, less than point, not less, sorry, more than 0.5 micrometer. It can have something between zero point 0.3 to zero point 0.5, that is 3, and something more than 0.2, that is 75, then more than 0.1, that is 35. So, but overall, the standard is based on 0.5 micrometer. That is how you see the numbers are matching. Okay, then only one is allowed. So you can understand how clean or how strict it is. Then going towards class 10, so 10 particles of this size in the same quantity are allowed. 100, it's class 100, 1000, 10,000, and lakh. They are equivalent to some ISO standards. Like one is equivalent to ISO 3, uh, 10 is equivalent to ISO 4, 100 is equivalent to ISO 5. So how are they related? Okay, how are they related? Let's see what is ISO standard, then you will be able to understand how are they related. So ISO is the International Standard Organization standard. So certainly here the units will change. There the unit was feet. Here the unit is in meter cube. Okay. So here the particle size is in terms of meter cube. per meter cube. So the larger volume, the particle numbers will be more. Okay, but here we can go to some even more stringent standards. Okay, there it was based on 0.5 micron. Here it is based on 0.1 micron size. Okay, so if there are 10.1 micron size uh, particles in a room in 1 cubic meter, cubic meter is much larger than cubic feet. Okay, then it will be called as ISO 1. If it is 100 particles, so that is 10 raised to the power 2, that will be ISO 2. Then comes 1000 particles, that is 10 raised to the power 3, and that is ISO 3. And you see this ISO 3 is equivalent to Fed standard class 1. Okay, so if we say that ISO 1 and ISO 2 will be even more stringent in comparison to Fed standard 1. Okay, so they are having some more stringent conditions, like more stringent particle size. Then comes ISO 4, 5, 6, then 7, 8, and 9. So 7, 8, and 9, they are of higher value. So here the definition is in terms of 0.5 microns. And then in case of ISO 9, that is in the case of that's based on 1 micron size standards. So this is about a clean room. So how a clean room look like how is this maintained? So if you see, this is a picture of class 1000 clean room. Okay, you see a lot of tubes are there. Everything is sealed. Then all the filtration techniques that are used, that is based on HEPA, high efficiency filters. Okay, they are used to clean the dust. There should be no dust particles inside it. Laminar flow of air is there. It is always maintained at a positive pressure. That means always the pressure inside this clean room will be higher than outside, so that nothing will try to enter in. Whenever if a door, even the door is open, the pressure will push something out. It will not take something in. So always a positive pressure gradient is there compared to what is in the case of sorry, what is in uh, outside. Okay, so compared to that, there is a positive gradient. So this is a class 1000 clean room. Now if we see uh, a better clean room, this is the entry point of a class 100 clean room. And class 100s are generally not maintained in a big room. They are maintained inside small chambers or fume hoods, you can say. Okay, so this you see is a class 100 clean room, and the whole area is not exactly class 100. Mainly this area is the class 100 clean room. Okay, this particular outside may be class 1000 clean room, and that particular area inside is maintained at a class 100 clean room. There is a laminar flow inside, so it might be that the corridor area is a class 10,000, the labs are class 1000, and some specific area where actual processes will occur maybe class 100. So that is why when we are taking these wafers and all, you have to seal it properly using put it in a desiccator and then transport, so that this outside environment does not affect it. Okay, so what to do when we are in a clean room? Okay, before entering the clean room, enter only through the anti room. That is, there is a separate room where you are cleaned with a flow of air, as well as to ensure that while entering, you don't enter directly. You wear apron and everything. Not exactly apron. You should wear the PPE kit itself. So there is a bench kept so that you don't directly enter. You have to get over it and then enter. Okay. Walk across sticky mats to clean soles of your shoes. So there are sticky mats before entering, you have to walk over it so that your soles are cleaned from dust. Wear shoe covers. Even after this, you have to put covers over it. Wear clean room garments like this. You see how people are wearing. Okay. Wear a puffed cap and beard cover. If you have a beard, everything should be covered so that these hairs should not go out. Wear gloves if you are going to work, or at least a covering should be there. Okay. And if you are taking any tool with you, you have to wipe it properly. Although it is generally not allowed to take some external tools inside, but in case it is necessary, you have to wipe it properly so that it is before it's going inside, it is clean. When inside a clean room, this is just to understand that how stringent these parameters are and how well it is maintained. Okay, so when you are inside, never ever remove any clean room garment. What you are wearing, you have to wear. You don't have to open it inside. No unnecessary paper products or paper bags because paper have some dust, can have some fibers that will affect it. No wooden pallets, ladder, or wood handle tools. Okay, everything should be plastic handled and these things. No cardboard boxes. Again, they have fibers. No pencils, no eraser, only pens. And that also clean room pens. They are kept inside. You don't have to take from outside. Never bring unclean or rusty tools. No food, no drink, no chewing gum ever. And no excessive or dangling jewelry. This is very important so that you are safe from accidents as well as you are not contaminating the work there. Don't raise your sleeve or observe your watch. There is always a wall clock kept inside the clean room. You have to check that one. Okay. So this we have understood that in what environment it will be done. Next is the wafer itself has what has reached you can be contaminated and it has to be cleaned. Okay. Why is the cleaning required? Because it can have some contaminants and solvents from the processes that like it was in form of sand and ingot we saw, right? It is sawed, it is polished. This can lead to some contaminants as well as some solvent stains like methyl alcohol, acetone, trichlorethyl, or isopropyl alcohol and xylene. These can cause stains over it. As well as when we are buying it, when we are transporting it, there can be dust from the operator and equipments. They might be traveling from different country altogether and coming to us. Okay. Then there can be some smoke particle that has small particles that has come over it. Okay. So there can be different type of contaminants. Those are either they can be organic material or inorganic material. Some of organic materials are like methyl alcohol, acetone, and these stains. Okay. Then some inorganic materials like some anions like anions and cation metals can be there. Some molecules might get absorbed since it is opened in the air. Something might get attached to it. So what are different sources that can cause this contaminant? They are the location itself, where it is being kept, the attire, even though we have taken care, there can be some contaminant, some construction activity nearby, even the electrostatic charge because particles get electrostatically charged. Okay. Then during wafer handling, how we are taking out using tweezers and all, they itself can have some contaminant. The furniture, the processing equipment, stationery, chemicals. The chemical might not be very clean, although in clean rooms generally uh, 5-9 purity. Okay, 99.999% purity is chemicals are used in general. Okay, the operator itself, humans are the best source of contamination. Okay, so they can also contaminate the source. So, in general, The wafer cleaning is divided into two types, dry cleaning and wet cleaning. So very obvious that in dry cleaning, so, so I think this is opposite. Okay, it will be wet here and dry here. Okay, so in wet cleaning, water is used. Mostly chemicals are used in which you are dipping something. Okay, and no, it is correct. Okay, then, uh, but in case of dry cleaning, the thing is that we can process single wafers only. Whereas in case of wet cleaning, we are putting a lot of wafers in, or a lot different wafers altogether, and at once the cleaning can occur. Okay, it is repeatable in both the cases. It is repeatable, but in case of dry cleaning, it is a batch process. It can not a batch process. It is single wafer process, and so it can be costly as well as the chemicals involved are a bit not that environment friendly, we can say. Okay, so the throughput will be less, but it will be dry, involving like giving better quality but slower. Okay, so in general, there are different cleaning methods. Some of the cleaning methods that are quite popular are RCA1 and RCA2. RCA1, that means Radio Corporation of America. It was developed in Radio Corporation of America. That's why it is named like that. Now it is even known as SC1, that is Standard Cleaning 1, and SC2. Then there is a method called as vapor cleaning or thermal treatment, that is baking at 1000 degrees Celsius in vacuum or in oxygen. Okay, plasma or glow discharge technique. So these are dry techniques. Okay, then comes mechanical methods, which means ultrasonic agitation, polishing with abrasive compounds, and supercritical cleaning. This is especially used in case of MEMS. Okay, where we have some mechanical structure or microstructure, deep structure, and when dust particle or some particle is going inside it, so it is agitated and take, taken out. Okay, we will see some techniques. Okay, like RCA1 and RCA2, these are the common techniques, so they are used in conjunction with each other. RCA1 will be done, then RCA2, both have to be done for the complete removal. In this case, ammonium ammonia uh, and hydrogen peroxide, uh, sorry, ammonia and hydrogen peroxide, they are mixed together with H2O in 1:1:5 ratio. The ratio can vary a bit. Okay, and operated at 80 degrees Celsius. And the this is a wet process. Okay, so all the wafers are dipped. Okay, this removes all the organic or polymeric materials. Whatever organic contaminants are there, they can be removed using RCA1. Then comes the RCA2, that includes HCl, H2O2, that is hydrogen peroxide, and water in 1:1:6 ratio. The ratio, again, I said, a bit variation can be there according to the process optimization. Uh, when you will actually work, you will understand that yes, that the chemical that you have is of what quality, and how much cleaning is there, and what kind of wafers you are getting, how much organic contamination is there in general, how much is not there, what is the like amount of metal contamination. Okay, these things will define, but slight variation, although the standard one is this. Okay, this again is at 80 degrees Celsius, and this removes metal contaminants. After doing this, you will see the surface become hydrophilic. If you dip it and take it out from water, you will see no contaminant, like no water there. It will just drop. This is the identification that it has become clean. Okay. Then there is something called as piranha cleaning, which is very commonly used. And seeing the fish, you might understood that uh, this is based on the name of a fish, piranha. Okay, that is able to that is actually considered one of the most dangerous fish in the world. I think there is a Hollywood movie based on this also. Okay, so this is found in Amazon basin, and these are small fish, and they can eat uh, human flesh itself. That is 80 kg of human flesh itself in 5 minutes. Like four, 500 small piranha will come and they can eat. Okay, so dangerous. And the piranha cleaning process also occurs, like works like this. That is why it is called as piranha cleaning. This is mostly used to clean organic residues. When the wafer is coming, someone might have mishandled it a bit. Okay, and organic contaminants, although they are already there, as well as the human itself is a big source of organic contaminant. So these things can be removed using piranha cleaning, most of the commonly used cleaning process. And there's a mixture of sulfuric acid, which itself is quite harsh chemical, okay, and hydrogen peroxide in ratio of 3:1 is made. When you will mix this, you will find that it becomes hot itself. You don't have to heat it, it's very hot. Okay, and it is very extremely corrosive to organic materials. So when you are doing this, it has to be handled very carefully so that no explosion or injury happens. So under guidance of someone who has already done or who already knows, is an expert, should only be done. Okay, and this cleans organic residues. Okay, it was first developed for cleaning utensils like very old utensils, but later on it was found that it is very effective in removing organic residues, and it was adopted in case of wafer cleaning also. Then there is something that I said, supercritical cleaning, in which case when there are some depths and some structures. So supercritical fluid CO2 in you, you can say CO2 is a supercritical fluid in the sense it can exist in liquid form and directly uh, like it can change its phase very easily. Okay, like it can coexist in all the forms. That is a supercritical fluid. Okay, at around 300 Kelvin. Okay, so supercritical CO2 is used for this cleaning process. This enables complete removal of organic as well as inorganic contaminants. But the problem is it will certainly be a costly process. Okay, it has liquid-like solvency properties. It will very easily dissolve anything, as well as it is existing in gas phase, so it will go in each and every point. As well as it is a bit viscous, that it is able to push the material out, the particle out. So this is a cleaning process. There is one, this these were cleaning process. But in between the processes, when we are doing, we might need to clean our wafer in a shortcut method, we can say. Okay. And for such processes, some degreasing. In degreasing means removing grease or organic contaminant very fast. Okay, from the silicon wafer surfaces. This process is used. So this is not a very perfect process, but this is something that in short, like if you have a wafer, you are doing one process, you want it to be clean. To ensure it, you just uh, put it through degreasing process. There are different kind of degreasing processes. One I commonly use is like we put in 50 degrees Celsius acetone. That is directly, it is not heated, it is heated in a warm bath. Like water at 50 degrees Celsius is maintained. Inside it, it is sonicated using ultrasonic waves. So something like where the contaminants are moved out by the help of ultrasonic wave, and in acetone, it will dissolve. Okay, then it is taken out from there and put into isopropyl alcohol for 10 minutes sonication, but this is cold. Okay, then put in DI water and nitrogen blow. Then it is boiled in methanol for if some extra residue is there at 80 degrees Celsius for 10 minutes, and then again DI rinse and nitrogen blow. DI rinse and nitrogen blow is something that will happen after every step. Even in some cases, some people even use it like heating at 100 degrees Celsius in isopropyl alcohol for 10 minutes, then DI water and drying. So there are some variations of this process, and they will also depend on the substrate used. Like in case of if it is flexible, acetone cannot be used. Acetone will, if it is not compatible with acetone, it might actually damage the substrate itself. Okay, so according to our substrate, according to our material, these processes can be a bit different. Okay, then comes something called as oxidation. Okay, this we will not go much in details. Okay, silicon is there, and silicon when heated will actually convert into oxide, SiO2, and SiO2 is a like silicon dioxide interface itself is said as God made, like one of the most perfect interface that occurs naturally. Okay, and so no extra effort to make the addition is there. Okay, so this addition itself is very good, God made addition, it is said. Okay, and SiO2 is some a dielectric oxide. Silicon is a semiconductor, we know. Okay, it can be used as a covering, as an isolation, like a lot of uses are there. So how is it done? uh, let's skip this. Yeah, so silicon oxide has an excellent masking behavior, so it can protect the layer below it. Then we have seen that there are p-type and n-type semiconductors, like, and how they are made? They are made by doping with boron, phosphorus, arsenic, or antimony. Okay, so it can even act as a mask for these common impurity species. So if you are filling just to you want just to dope in specific area, you will cover the other area with SiO2. So it is a very good mask. And how we will cover selectively, that we will see later on. Okay, it is a very good electrical insulator, so can be used as a separation between two electrical lines also. Very high breakdown field with excellent junction passivation. Okay, Si SiO2 interface always result into electronic trap level and some negative interface charge that makes it very stable interface, you can say. Some charges are trapped and some negative interface charge is there, that leads into this good addition. Okay, it has very stable bulk electrical properties over a period of time, so it will it is not like today it is showing this breakdown field, some days later it will show something else. It has very stable material properties, electrical properties over a period of time, and very stable interface, and always same, like very controlled growth can be done, very precise understanding of this interface is there. Okay, that is why this is very important. So, and one interesting thing is that this oxide will not uh, like when we are growing it, there is two different things. When one is when you are growing oxide, and the other is when you are depositing an oxide. Here we are talking about growing an oxide or oxidation. So the silicon itself will get consumed and make the silicon oxide. So it is said that if 1 micrometer of silicon is consumed, an extra 1.25 micrometer will be formed. So total 2.25 micrometer will silicon oxide will form from 1 micrometer silicon. If you do the calculation of the atomic mass and volume, you will find that this is empiric, like this is fitting empirically also. Okay. Total. Okay, this chemical reactions will not go into. Okay, so as I said, it is like 45% and 55%. So 45% of the like what is the total SiO2, in that 45% of it was the actual silicon, and after adding the like after the oxidation, it grew and it became this total 100%. So if someone asks like you can do this unitary method and other reverse division, and you can find out how much silicon was used to make this much silicon dioxide, and in case you want to grow say uh, 1 micrometer thickness of silicon dioxide, how much of silicon will be used. These things we can this okay. So there are two different ways of oxidizing this silicon: dry oxidation and wet oxidation. Oxidation, that means certainly there will be oxygen, but what will be the source of oxygen, that will determine what type of oxidation it is. If it is a gaseous oxygen is given, then it is considered as dry oxidation. This whole process will occur at a very high temperature, mostly 800 to 1200 degrees Celsius. Uh, in general, like our furnace, we are using at 1100 degrees Celsius. Okay, so you can understand it will, these reactions will occur at very high temperature. Then there is wet oxidation, that is H2O. When water is being used as the source of oxygen, then this one is uh, sorry. When water is being used as the source of oxygen, then this is called as wet oxidation. So seeing this, like you can say, okay, why to go for wet oxidation when we can directly give oxygen, right? But the wet oxidation process is much faster compared to dry oxidation process, slower. Why? If you see the size of O2 and H2O, hydrogen is a smaller molecule. Okay, two oxygens, like let's say two oxygen molecules are there. Okay, and one oxygen molecule with two hydrogen. Okay, so this H2O is much smaller in size. Like the reaction is not occurring at the top. First layer, it will convert into oxide, and then the second layer, like the species has to go inside. So the diffusion, it is mostly diffusion control. Like I skipped that part, will not go very much technical. Like this course is not that technical in sense of microfabrication, so we'll just be covering the overview of the process. So understand that this molecule is smaller in size compared to O2 molecule, so it is easy to diffuse inside, and so the reaction is fast. But along with this, there is one very big difference, that is, in case of this dry oxidation, SiO2 is the only product, whereas in case of wet oxidation, SiO2, that is the output we want. Along with that, some hydrogen molecule is also released, and this makes the film not that of good quality, not of that good quality. So faster, but since it will diffuse out again, so this will uh, create some imperfections. Okay, so in general, what is done is that process of dry, wet, dry is followed. Top and bottom layers, the best one we want is dry, and in between for fast oxidation, we go for wet oxidation. Okay, so how these furnaces look like, if you see, these are the furnaces, like these are different furnaces where this wafer, this is the whole set of wafer, like board, quartz board, on which these wafers are stacked and then put inside and then baked for some specified time which we know, and this is the controller. Like inside that, the furnace, how much will be the temperature. Then gases are put, either H2O or uh, nitrogen with nitrogen with H2O. Like water cannot be put inside, so moist air is flowed, or direct oxygen is given. One more advantage of using wet oxidation is oxygen, uh, like the flow of oxygen can not be very easy to maintain, whereas in case of like bubbling through, the flow rate can easily be brought down, and slowly we can put the air. We don't waste a lot of air inside, like oxygen inside it, and it is handled very carefully. Like if you see how hot it is, the quash tube and all, and then it is taken out, is pushed in very cautiously. Okay, then come one important point. Like till here, something I think I covered things which were not that much covered in our classes. Now comes something that we have, in fact, covered a bit in the class. That is thin film deposition. So in once we have our wafer, it till now we were talking about silicon wafer. This same thing can also be replaced with some other materials. Nowadays, we have a lot of materials that are being explored. Okay, but silicon is something that is quite standardly used. A lot of good techniques are available. That is why silicon is preferred. But the next processor will remain same for any other thing also. That is film deposition. Here we were growing something from the wafer itself. But what if we have to put something extra over it? That is a film or a layer of a material over our substrate. The substrate can be silicon or flexible substrate like polyamide and these things. Okay, then there are two categories of thin film deposition. One is chemical vapor deposition, that includes atmospheric pressure chemical vapor deposition, low pressure chemical vapor deposition, plasma enhanced chemical vapor deposition, high density plasma enhanced chemical deposition, and the other is physical vapor deposition, that is evaporation or sputtering. What is the difference between these two? In chemical vapor deposition, the deposition will occur as a result of some chemical reaction. So, two different species or three different species will be there, and they will react and form the desired species, desired material to be deposited. That process is called as chemical vapor deposition. So, these chemical reactions will take place and they will facilitate the deposition. In case of physical vapor deposition, the material that we want to deposit, we have the material, but like we cannot directly put it on the wafer or substrate. So that has to be transferred using some specific technique. And the most common one is like heating it too much so that it evaporates and it uh, deposits over the substrate. Or sputtering, in which case we are hitting it with some ions and or plasma and removing the material layer by layer, molecule by molecule, and then depositing over our desired substrate. Okay, we will see some type of this. Okay, so the difference, like some of the PVD methods are thermal evaporation, so where we are heating it thermally, electron beam evaporation, where we are uh, like where we are evaporating it using electron beam, like a beam of electron. Instead of in thermal evaporation, a high current is being flowed so that it heats up and then it evaporates. So it is basically a resistive heating. Okay, whereas in case of electron beam evaporation, an electron beam is focused over it and then it evaporates. Then comes the sputtering. As I said, the material, like target is there, it is being hit by some other species and it evaporates. Not evaporates, it transfers from the target to the uh, to the uh, substrate. Okay, this slide I think we have discussed in one of the previous class also. Okay, you can see those. Okay, in all these uh, cases, you see contamination control is very important in all the processes. So wherever we are talking about microfabrication, we must take care that no contamination should occur in all this case. And the measurement is done using, in case of thermal evaporation, we are using quartz crystal monitor to measure the film thickness during deposition. After deposition, we can measure using other tools also. But during deposition, ongoing rate of deposition is measured using quartz crystal monitor. Okay, so what kind of films can be deposited using the physical vapor deposition? Metal, alloys, dielectric, ceramic, semiconductor, inorganic compound, and polymer. All these can be deposited using physical vapor deposition, but they should be in their form and there will be no chemical change. It will just be physical vapor deposition, only change of state. No change in, no chemical change. Okay, that is the difference of PVD and CVD. Where there is a chemical reaction or chemical change occurring, then it becomes CVD. Okay, so let's say we have some material for deposition. Like there are different materials. Like they can look like pellet, they can look like tablet, they can look like powder, they can be small pieces of metals and these things, and they can be deposited. Okay, how? Thermal evaporation, sputtering, ion plating, cluster deposition, laser ablation, like there are a lot of physical uh, vapor deposition techniques. I have summarized this in this table. Like you can see in details about this if you are interested. Like what are the advantages, disadvantages. In fact, two very common ones are thermal evaporation and sputtering. Thermal, it is the relatively low cost and simplest method, mostly used for metals. Okay, aluminum, chromium, gold, silver, molybdenum, tungsten, these things. Okay, but coating addition is not as good as compared to other PVD process. Second one is sputtering, better addition than thermal or vacuum evaporation. Okay, can it can even be used to coat compounds. Unlike this, where only metals were possible, here some compounds can be used like Al2O3, TiO2, silicon nitride, TiC, TiN. These things can also be used, but slow deposition rate and more difficult to control, very difficult to control the rate of deposition. It will start slow, go very fast, might get slow. So a lot of optimization is there. Okay, then there are some more techniques that are nowadays becoming more common, that is ion plating and cluster deposition, laser ablation deposition. This is something that has shown some positive results. Then aerosol deposition. These are some of the techniques that are used in case of PVD. Okay, PVD and is where there is no change of uh, no chemical change. So if we have to deposit Al2O3, we will have to have Al2O3 with us. It is not that we will have aluminum uh, something and then some oxide and then we will do some chemical reaction. We will have to have aluminum oxide, silver, gold. These things we will have to have, and that we will coat. Okay. So let's see how, let's see some example of uh, this PVD. Like these are thermal evaporation instruments. I will show the one that we use in our lab also. Okay, it is mainly used for metals and very high vacuum is needed. Why a very high vacuum is needed? There is something like contamination we know that will be removed, like we will remove all contamination. Second thing is that when we are evaporating these materials, like there is some material that is being evaporated from here. If there is some obstruction due to the Brownian movement or like some collisions, it will not be able to travel straight, or mean free path will be less. Okay, so in short, to have good deposition, less number of collisions between these molecules, we make very good vacuum. Like all the things, or even the air particles, we try to remove before the deposition starts. Okay, so thermal evaporation can be different type, like it can be based on cat like it can have electric arc based, it can be crucible based, where it is resistively heated. Okay, low as I said, low working pressure or very high vacuum to increase mean free path. Low surface damage is there, so in this case the material is just evaporating and depositing, so it is not having a lot of energy, it is not having just, yeah, it is not having some energy that sorry, that will penetrate inside the material. Okay, that is why it is having the low surface damage much faster compared to sputtering, but there are limited number of materials that can be deposited during thermal evaporation. Then there is something called as shadowing. So if we are trying to deposit, suppose we have a structure like this, we are trying to deposit it, but we can, if we are just putting it and it is going there, it might not lead to proper coating, uniform coating, but we want uniform coating. Okay, so what is done is that to get a uniform coating, it is heated and rotated. The substrate is heated a bit and rotated so that good adhesion is there, as well as we get uniformity in it. That results into good uh, like uniform deposition. Okay, and this shadowing effect can be overcome. Okay, mean free path, let's know. There are like when we are discussing this, there is something called as unit of pressure that is very important here, because uh, since most of the instrument come from different maybe like different, they have origin, different origin, and in different part of world there are different unit pressure, so you will get different units of pressure in different instrument. So to understand it, you must know that these all are unit of pressure, and pressure like mostly relevant while making the vacuum and this. So 1 torr is equal to 1.33 millibar. That is the atmospheric pressure. Okay, 1 bar is again equal to 750 torr. 1 bar equals to 100,000 pascals, and one atmospheric pressure is equal to 1.01325 bar, or 1 torr. Okay, fine. So these are units of pressure. Now I will show you some thermal evaporation systems that we have. Like this is one from Semicore. This is almost automated, having uh, two boards, I think. Yeah, having two boards. So this system, if just to appreciate how it looks like, this is the part where uh, like the back you saw, that is the turbomolecular pump using which we make this high vacuum. Okay, this is the controls unit. It is a bit complex, like inside below it, since we have to go to very high currents to melt these metals, like transformer is there, and this whole system is chilled. Uh, so the, yeah, you see this. pump is there. Then there are tubes you see, as well as this thick wires that are used to carry such high amount of current, as well as this whole system has to be cooled properly using chiller that is very like almost equal to this instrument itself, the chilling unit that is used to cool the whole system, the gun, the crucible area, so that other parts are safe. Only the area that needs to be precisely heated is the one heated. Then this is a simpler thermal evaporation system that we also use. On the right hand side, this is the load lock chamber, like so that we don't have to change the like disturb the vacuum every time. So samples are put inside there and then shifted towards the high vacuum area. So you see this is the control panel, different switches. This is the whole setup, how this system works. Behind you will see that there are, yeah, this small opening. This is used to see what is going inside. During during normal processes, you will not be able to see. Only when evaporation occurs, you will be able to see. These are high current transformers to carry such high current. So you see it is a web of a lot of tubes and all used to control the system. Okay. Now if I show you one video from one deposition where I'm trying to deposit some different materials over. So if you see it, see the upward, the up, something that is moving, that is the substrate, and this is uh, the metal that is gold being evaporated. Like it is in molten state at present. I'm filming it from a distance through that window, so it might not be very clearly visible. But you see how it is boiling this material and then evaporating and depositing over the material above. Then some when I am saying that I am putting aluminum, chromium, and gold like different stacks, so something might come to your mind. What will be the structure of stack? So like when I bring it down, what will be on top? Below it, what will be? Okay. Then what is the purpose of using so many materials? Okay. And why exactly this is the sequence? Can I not change the sequence and all? Okay. So there are some reasons like we cannot directly get we cannot put one metal and directly get the good conductivity, because there can be uh, some difference in work function. So that is one reason. Other reason is that we need good adhesion. Like suppose we want to deposit gold over it, but we might not get good adhesion with gold. Okay. So in this case, we are using some material that is, you see that whole thing was happening inside that, and we are able only to see like when no deposition was happening, you see that that opening was black, like nothing was visible. Only when deposition is happening, then we are able to see the structure. Okay. Chromium is generally used below gold. Chromium or titanium, that is for good adhesion. Okay. Good adhesion of gold. Okay. Now we will come to something that is sputtering. You saw basic overview of PVD processes we are seeing. Okay. So in this case, there it was in form of pellets, small pellets, powders, and these things, so that it can be evaporated. Now, in case of sputtering, the materials are to be formed of target, or you can say uh, tab not tablet form like this size, and coin kind of form, uh, big coin kind of structure. 2 inch. These are 2 inch. 2 inch. This is PT is of 1 inch. Okay, based on the gun or the structure of the sputtering, the point where we are putting the magnetron gun we are using, that will define what size it can take. what thickness it can take. So they will be in this form. Like you see, this is PT, this is zinc oxide, this is copper, this is tantalum oxide, titanium oxide. Such materials can be deposited using sputtering. So it has better coating adhesion than vacuum evaporation, can even coat compounds like Al2O3, AU, copper, chromium, and these things. This is one system that we have in our lab. Okay, you see there are four guns. Okay, this gun was not there that time. Now we have four different guns. Like we can deposit four different materials at the same time inside it. Again, this will also not be visible once the deposition start, once the plasma form. In this case, argon plasma is used. Okay, so what happens is that gas, in this case also we go for good vacuum, very good vacuum, and then we purposefully insert some amount of argon in it, and then we create a plasma of it. And why is it so? Because argon is a heavy molecule and a novel, like it is a novel gas, as well as it is generally heavier than the molecules that we are trying to deposit. Okay, so we are inserting argon, and we will create such a good, like we will get so high voltage, positive and negative, that it will create a plasma, that is ion of the argon itself. And this will get, since it will be argon positive ions, so it will go towards the negative electrode. And here our material, say Al2O3 is kept. No, high voltage is there. No? So let's say aluminum is kept. Okay. So it will come and it will strike it. Once it strikes with so much energy, it will knock out some material, and it will get its electron, and it will again convert into argon. Since there is negative charge is there, it will get its electron. And then these materials, which now are electrically negative, will flow towards the positive electrode where we have put our substrate, say silicon or all, and they will get deposited there. They will leave the electron there. So in a sense, if it is connected to a power source, okay, the circuit is getting completed by this molecule, by the plasma being generated, and the circuit being completed. So in a sense, the deposition occurs with the help of argon, and argon is not used. Here also, no change, no chemical change, only the phase is changed. Like the uh, gas are gas is changed into plasma and back. Okay, as well as the materials are, the molecules are taken out in form of molecules or ions, and then deposited there. Okay, so mean free path here will play a very great role. So you see here, this is plasma is generated, how metals are being deposited. Let's skip. Yeah, you will be able to see this. This is the system that is what. Okay, so in our case, yeah, this one is the turbo, like used to turbo molecular pump used to create such high vacuum that we design. That one is the rotary pump, that is to support this whole process. Okay, so, and this right side, this is the load lock chamber where we are putting our sample, and then we are using this magnetic handle, we are shifting inside. Okay, so using this handle, magnetically controlled handle, we can shift the material inside. It has already been shifted here. Okay, inside it, you see on the top here, we have the samples. Below, the gun is there. In that, we have the material, the substrate. Okay, then now, since we are doing it for research purpose, we are not using the whole wafer. We are just using small cut part of wafer. We are putting this sample inside and we are sifting it inside. Then this is when plasma has the first one I was using a light source to show it. Here there is no light source. The plasma is that glow is from the argon plasma that is occurring, and it is depositing the material from this gun towards the, you see a concave kind of plasma is formed, and that is depositing the material onto the substrate. So this is the process. So there, if we compare between these two, evaporation there are low energy atoms. Sputtering, it is high energy atom since it is ionic in form, so it may even penetrate inside, like it may result into some kind of doping or impurity. In case of evaporation, there are fewer collisions, and it is line of sight deposition, so very close. And there is no gas in the film since we are doing the deposition at very high pressure. Whereas in case of sputtering, it is a comparatively lower vacuum process, so more number of collisions will be there, less line of sight deposition. Okay, and then there will be gas in the film also since some gas is already inserted. Evaporation, the deposition rate can be controlled in a wide range, like different range of deposition rates based on the evaporation rate we can control. Whereas in case of sputtering, it is very much process dependent. Like it is not, we cannot do a lot of things. Uh, power power will not change much. Like pressure and it, like lot of variations cannot be done. Okay, but in case of evaporation, the grain size is larger, whereas in case of sputtering, smaller grain size, so smoother, like the film will be smooth. Okay, in case of evaporation, there is less, like less number of grain orientation, whereas in case of sputtering, there are many grain orientation. Sputtering have better addition since it is an ionic uh, moment is there, whereas in case of evaporation, it is physical, only physical, purely physical. Okay, so that is having a poor addition. Now comes CVD process. Okay, so we have seen how sputtering occurs. Now, in case of CVD, like in case sputtering and thermal, we might not be able to get the material that we wish. Okay, so we go for chemical vapor deposition, where chemical processes are used to do the deposition. Okay, it is somewhat chemical reactions are taking place and then deposition is happening. Okay, the materials are adsorbed on the surface, and then the reactants are adsorbed on the surface. The reaction occurs, the byproduct moves out, the material remains there. That is the process of CVD. There are different kind of CVDs. If you see, this is APCVD, that is happening at atmospheric pressure. Then low pressure CVD, this is happening at lower pressure. That means at a bit lower pressure. But all these are furnace kind of structure. They will be having furnace, and they will be used to create the like facilitate the reaction. Okay. Then plasma enhanced CVD. In that case, plasma is used to increase it. Then high density plasma. Again, the intensity of plasma will be high, and it can even be used for lower temperature deposition. So 150 degree or something. Sometimes in CVD you go to 800, 900, 1100 degrees Celsius also. So this thing can be done at a lower pressure by the help of plasma. Okay, now we will see what is lithography, one of the very important processes in microfabrication. So to understand what is lithography, you see this small video where one mask is kept, paint is applied, then another mask, paint is applied, remove. Another mask, paint is applied, remove. So you see different patterns can one above another, and in all these cases you see there is one plus mark or something that is being used again and again. That is a marking to align one mask over another. And this is the same process that is used in case of lithography, and multiple such layers. Like you see this material, like multiple layers are being made using lithography, and this is one of the most important part that is used in case of uh, microfabrication. So there are mainly two type of lithography: photolithography, that is based on light of 365 nanometer and 405 nanometers, or electron beam lithography, where electron beams are used as the source of exposure. We have seen a bit of lithography earlier also, right? So to understand photolithography, it is something like a very critical step where light is being uh, a silicon substrate is there. We want to pattern it. That is made using. Wait, there should be a video here. So here light source is used to pattern. Yeah, a photo mask is used to create the pattern over this wafer. And how is it done? We will see that. First part is preparing the substrate, that is cleaning the substrate. We have to do the deposition if we are depositing with PVD or CVD. Then we apply the photoresist. Photoresist is most critical thing here. We have seen about positive and negative photoresist, right? This is a critical thing. Okay. Then exposing this photoresist to light under the influence of mask, like the pattern we want to make. Then taking this and putting in the developing the photoresist, that is the area that we want will remain, other will be removed. Then etching the substrate and removing the photoresist. This is the simplest process. Okay. So you see this mask for the pattern is designed using computer softwares, and then it is made over a glass with uh, chrome materials over it. So this is a mask you see on the top. Okay. So photoresist, it is taken out and put put over this and rotated. You see above it is poured and rotated. That will create a very thin layer of photoresist over it. Then using this mask, not mask lamp, the alignment technique, we are putting a photo mask over it, a mask over it, and then we are putting some light over it, and that will UV light, and that will expose the area that is not covered by this mask, and that then we will have a pattern that is like that can be developed inside it. If we are putting it in the developer, that area will get removed, the other area remains. Then uh, if you see this wafer, then it is coated with gold or something, and at last the patterns are made over it. Okay. So this is somewhat a clean room, how it is being made. Like such yellow rooms are used to do this whole process, so that this cannot be exposed to something, some external light. Then comes the last process, that is etching. That is how you are removing. You have deposited, you have patterned, but how you are removing it. Okay. Again, this etching process is of two types: wet and dry. In case of wet, we are just like we learned about cleaning, wet and dry. Here, when we are using wet chemicals, where we are putting it inside wet chemical, that becomes the wet etching. That can be isotropic, and isotropic will not go very much details into this course. I think that will become a bit complex about. Okay, and then the process steps, like we saw, cleaning, masking. Masking is done using lithography, then etching, and then again cleaning. That is PR stripping or removing the mask. Okay, so the process is very much similar to oxidation and cleaning, where diffusion of reactants occur. It takes out the material, like reacts with the material and takes it out in form of reactant products. Okay. In case of this etching, the selectivity is very important. It should not etch the mask. It should only etch the material that we want to remove. This is something very critical. It should not be it is removing everything. Okay. Its selectivity, anisotropy, it should etch in one direction, not in multiple direction. This is also an important aspect. These things are taken care when we are selecting what kind of material to use in these things. So there are different kind of wet etchants. They are specifically used for some specific material, and they, like you see, these materials can etch aluminum, silicon nitride, and metals, but it will not etch SiO2 or silicon or PR. So we can use it for on a silicon substrate with SiO2 or PR as a mask. So these are the things that we have to select. There are some specific material that will etch only one direction. This is also so specifically for silicon, but here we are not concerned about silicon. Okay, we will move that. Then comes dry etching. This is somewhat very less selective. Like we are putting a mask, a physical mask, and then we are using plasma or such things to remove the material. This is dry etching. So they can be plasma etching, reactive ion etching, deep reactive ion etching, ion beam etching, or vapor phase etching. Okay. So in case of vapor phase etching, that is very highly selective, low damage to substrate, and ability to etch very complex MEMS structure and these things. Commonly used in fabrication of MEMS devices, semiconductor devices, and sensors. Okay. It is much faster compared to other etching processes. And these are then plasma etching, very similar to the supercritical cleaning, okay, where it can go inside using plasma and then it is cleaned. Then there is ion beam etching, will not go very technical into it. So just understand that there are different type of etching processes. Reactive ion etching and deep reactive ion etching are one of the best processes that you can observe. Okay, these are to make very small critical structures and all. Okay, so that's all. See you in some other course, next course.